All right, welcome back. Oh, coffee. We need the coffee. This first, then math. So 4.1, we're going to continue doing limits. I'll give you the definition of the idea of what we're doing with the limit. We'll give you the limit laws and when we're approaching a finite value and the limit is approaching a finite value. That's the most familiar case. And then we have to do where it blows up and we say equals positive infinity or equals negative infinity. And then we have to make x go to infinity. Long story short, there's a bunch of cases. We'll go through each kind of limits. There's going to be 4 cases roughly. Oh, that one's an old coffee. That old coffee that got gross. I've had a cold for like a week, so that's why on top of everything else, I think the mic level should be good. But let's do this. We're going to say that this symbol, the limit as x approaches a of f of x is equal to L if and only if, not using the precise definition, just intuitively, if values of f of x approach L as close as you want as x gets arbitrarily close to a in some interval. What we're going to say is x is going to approach a is the shorthand we've used, and we use it here. And then here we're saying equals. They should just use the arrow also, but what we mean by this is technically f is tending arbitrarily close to L. And then we write this symbol to denote this guy. And really algebraically, I did it all algebraically first, but we want, if you're not picturing the graph of a function near a value and seeing what happens, you're doing this wrong, I always say. So draw a picture is the point, is what Mark is going to tell us. And then if I have the graph of f of x, which we cheat and just say f of x, but there's the graph now in the plane. What we're going to say is as x approaches a as close as we like in the horizontal, our function may approach some value L as close as we like. But that might not be defined and you might have a hole. So what it's saying is you can get arbitrarily close to that value, but you can't actually touch it, and we can get arbitrarily close to a. And then we're going to have 4 cases now based on x can actually approach a, can be a real number, or a can be plus or minus infinity. My color's running out. Don't run out color. Is this one good? Okay, red's got some. And this one's going to say we're going to have 2 cases based on whether L is a real number or whether L is equal to plus or minus infinity. And so there's going to be 4 cases based on whether we're going to approach a finite value in our domain or whether we're going to push x to infinity, limits at infinity in the positive and negative direction, or we have to combine this with our function can approach a finite value, or it can blow up at infinity like 1 over x or 1 over x squared, etc., etc. Let's go through the cases one at a time. If we have case 1, we have a finite limit. That means L, so that's the function f of x at finite values. Oh, there it is, finite values. And that means to x. So x is going to approach an a, which is a real number, is what they mean by this, and f of x is going to approach a limit L, which is also a real number. That's what they're talking about. So finite limits at finite values are the ones that you're going to want, and hopefully that there's, even if it looks like there's a discontinuity or a trouble at the value we're going, there will be clever algebra that will clean us up. And so let's see how to do that. Let's do, for example, compute or state why it doesn't exist. Then we're going to have the limit as, let's do as h approaches 0 of x plus h squared minus x squared over h. So compute this or state why it doesn't exist. Does not exist. I'm not writing that out every time, so DNE. This is a limit. We're doing wax on, wax off. We're actually doing a limit or a definition of derivative through a limit. Of course, we're doing a limit. We're doing a derivative right now. What does this actually say? Well, we're going to use clever algebra. I look at this. The first thing I say to myself is, where are we going at the finite value? And we have to, so we're approaching a value. I've switched to an h instead of an x. So sorry, don't be confused here, but they might change the variable. So I'm looking, and I look, and h is going to 0. And I do have h on the bottom, which is a problem. We'll do a bunch in x in a second also. If there's clever algebra that can get me out of that, it's going to go to a finite number, and it will be a finite limit. The limit will go approach a finite value at some finite value a. Let's try this. The idea of this is to expand everything. So I have the limit as h, not x this time, as h approaches 0 of, now I can expand this, x squared plus 2xh plus h squared minus x squared on the top, and then I have over h. The idea is to get an h out of the top so I can cancel it with this, and then there won't be a problem anymore. That's the idea. And sure enough, it does. I can cancel this with this, and then I rewrite out my limit, and I see that I have an h. If you can't already predict this, I have an h in each one. So this is equal to the limit as h approaches 0 of h. Here, I'll write it out slowly. 2xh plus h times h squared over h. So I have an h in each one. I'm going to factor it out. This is the limit as h approaches 0 of h times 2x plus h over h. Now I can cancel the h, which is the clever algebra. If there is clever algebra, this will go away. This is what you like. Cancel, cancel, be clever. And then we get that this is the limit, and then this is the limit as h approaches 0 of 2x plus h. Once it's a polynomial in h, and this is just we're viewing it as a constant, this says that we can just put 0 in there, and we get 2x. What we computed there essentially was a derivative, but the moral of the story is we have case 1. Why are we doing limits? Eventually I'm going to show you that this was a derivative of x squared, and then we're going to show how to compute these things. But the finite limit was this guy, which is just a finite number, plus or minus. It's not plus or minus infinity, and that happened at a finite value. So this is a finite limit at a finite value. Let's do one more in x, so that I switched it to h accidentally, and I might have confused a little bit, but let's just do an x1. All right, the limit as x approaches 1 of x cubed minus x over x minus 1. I'll make it fairly easy at first. We're going to have to do a little bit of factoring and be clever, but they can hide a whole bunch of clever algebra in there, and that's why you're supposed to be good at factoring and be doing clever algebra, because we have to do it in the limits now. Again, I assess every time. I won't write it every time. Compute the limit or state why it doesn't exist is what they're asking every time. In this one, I look and I am going to 1, and then I do have a problem because I say 1 minus 1 is 0, and I don't want to divide by 0, and this would be bad. So if there's any justice, and it's not going to blow up and give us the next kind of limit, which is infinite limits at finite values, which means our function blows up when we try to approach a value, which we're going to call a vertical asymptote eventually. This is going to be algebra that will get us out of this. And let's start going. I see I have x in both terms, so let's factor the x out first. This is the limit as x approaches 1 of x times x squared minus 1 over x minus 1. And then this should hit a Pavlovian nerve. This is a difference of squares, so this is equal to the limit as x approaches 1 of x times x plus 1, x minus 1 over x minus 1. This cancels. And we get, I'll write it out one more time, but now that we have just a polynomial and we don't have a problem, we can put the value in. This is the limit as x approaches 1 of x times x plus 1. So this is going to go to 1, 1 plus 1, which is 2. So this is the finite limit 2 at the finite value 1. Even though that seemed like there was a problem, I used clever algebra and factoring techniques to cancel that discontinuity in the algebra, and so 1 isn't in my domain, but the limit, the function is still getting arbitrarily close to 2 as x gets arbitrarily close to 1 near that value. Let's try that when the things that you start not liking before we do at infinity. Let's do the next case where I have a trouble there, but it doesn't go away with algebra. What do we do? And then we'll give all the rules. I'm using the limit laws, so let's do that now. Before I do the next case, limit laws, whether it's positive or negative, but we're going to say, suppose that the limit as x approaches a, whether this is plus or minus infinity 2 of f of x equals L, and this might be plus or minus infinity, and then say that we have another function, limit as x approaches a of some other function g of x. Still at the a, we're looking at a, what's happening, and this might be m, so it goes somewhere, some other value, so finite limits at finite values, but it looks like that, but this might be plus or minus infinity, and this might be, so it's sort of all 4 cases. Then the basic things that you can do is you can add and multiply and divide and do all the algebra with limits is what they're going to say. 1, you can do the limit as x approaches a of a constant, first of all, times f of x is going to be k times the limit as x approaches a of f of x, which is k times L. So you can pull a constant out of limits. It doesn't mind if you do this. 2, you can split sums or differences. So I'll write it and be lazy as plus minus. The limit as x approaches a of f of x plus or minus g of x is equal to the limit as x approaches a of f of x plus or minus the limit as x approaches a of g of x, which they'll write as L plus or minus m. So you can split the sum. The limit of a sum is the sum of the limits, is what you can do. And then you can also do 3, and 4, you can do division, etc. So the limit of a product is the product of the limits. The limit as x approaches a of f of x times g of x is the limit as x approaches a of f of x times the limit as x approaches a of g of x, which will be L times m. And the limit of a quotient, the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f of x. Sorry, I should have drawn that a little bit smaller. The limit as x approaches a of f of x over the limit as x approaches a of g of x, which is L over m, provided m is not 0, of course, in that limit in this case, because we don't want to divide by 0. And there's a couple other ones, but the other one that I want to squeeze in that we should have is 5, and there's a few where they do nth root, etc., these types of things, and polynomials. Maybe I'll do all of those ones, but we should just say that there's certain limits that we want to know, and one of them, well, we don't have continuity. So for now, let's just leave it as this. We can do the other ones that they list is they're starting to prep you for polynomials, is what I'm thinking. So if we still have those 2 limit laws, they'll also say that the limit as x approaches a of x is a, and the limit as x approaches a of, if a is a finite number, of x to the n is a to the n. And then you can combine the limit laws already. Number one and this one are going to tell us that the limit as x approaches a of a n times x to the n is a n times the limit as x approaches a of x to the n, which will be a n times, oh, we should have used a capital. Now I'm thinking of polynomials now. But then I used a n and little a, bad notation. So this is a n the coefficient times a to the n the number. And so basically what we want to do, and then we can split sums, and so we can take limits of polynomials, we can take limits of rational functions with those limit laws. Now if you have a polynomial which is a n x to the n plus dot 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 plus a0 over some other polynomial b n x to the m plus dot 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 plus b0. So you have two polynomials. You can, if you're taking the limit of that as x approaches a, what they're saying is you can put the limit onto the quotient, then you can put the limit onto all the sums, then you can put the values. So as long as there's no problem, you can just evaluate and put the number in and start computing. And so what we're going to do is we're going to do our Rolodex. Once we get expressions like this, we're going to use the limit laws, which I've already been sort of using and cheating a little bit. Now that we have them explicitly and I've told you them, we can systematically apply them. The only problem is when we're approaching the value that we're going to, if the bottom gives us trouble, etc., then we have to check out what's going on with that. Let's see what happens when it does give us trouble now. Case 2 is infinite limits at finite values. So what I mean by that is, for a picture of that, f of x is going to approach plus or minus infinity. It's going to blow up. And do I have another color that's actually going to, no, he's going to be almost dead. Oh, that one's totally dead. I should have checked before. The one pen was starting to run out. So this one is going to say x is still approaching a finite value, where this one's still in R. So we're still going to approach a finite number, but now say that value isn't in the domain, and we're going to get what we call a vertical asymptote. So before we start, you want to think of the standard functions. 1 over x. 1 over x looks like this, and 1 over x squared. And so what we're going to say is at 0, 0 is not in my domain because we have division by 0. And then we're going to check, and this is saying it blows up. And so we're going to say this one's positive infinity, and this one's called negative infinity. And then here, it looks like they both go to positive infinity. So then we're going to have to start looking at, this is a good segue also into left-hand limit, right-hand limit, and how we're going to do this type of business. So let's talk about that. Finite limits at finite values. Before we do that, we need to check left-hand limits and right-hand limits. And this is a good segue, because this is where we want to start saying, okay, it was blowing up, and if we have certain odd cases and even cases, even with those two functions that I drew, and we're going to say that the one on the Atari function is going to technically equal positive infinity because they both went the same direction, and then the other one was going opposite direction. So we're going to use left-hand limit equals the right-hand limit if and only if the limit exists. What is a left-hand limit and a right-hand limit? We're going to write the limit as x approaches a above for f of x equals L, if and only if what we're doing here is now you're only allowed to approach the a value from above. This is the plus. So we're approaching from above. When we do it the other direction, it's going to be a will be here, and you're allowed to approach from below. So we'll write negative. This will be the limit as x approaches a below of f of x equals L. What does this mean? This means if and only if f of x gets arbitrarily close to L. I'll even write it in our lazy symbol, but our function doesn't touch it, but it tends towards L arbitrarily close as x gets arbitrarily close to A from above or the right. That's why we call it the right-hand limit, or above the value. This symbol is true if and only if, because then this is what you're going to have to do and what you're not going to start liking, and the algebra is going to get nastier. In the first ones, everything we just used algebra and factored everything out and then cancel, and we get a number. Now it's blowing up, we're saying, so quite often we have to look at what happens when we approach from above and when we approach from below. If it's different, we say doesn't exist. If it's the same, we say equals positive infinity, etc., etc. So this one is saying that f of x is still approaching that value, but now it's as x approaches A from below. So from below, I'll say, or from the left. That's what we're going to start analyzing. And then I'll state that one result is this limit, the left-hand limit. We're going to call this left-hand, no, this is right-hand limit. Right-hand limit. And this one's left-hand limit when we approach from the left or the right. And we're going to say that the right-hand limit equals L, and the left-hand limit equals L if and only if the limit is actually L. That's the one result we need from this. Then we'll get back to case 2, and we'll show you how it's quite often good to split into the two cases. So theorem. That one's almost done. The left-hand limit, the limit, here, actually, let me write it like that. Left-hand limit, which is equal to the limit as x approaches A from below of f of x equals L, which equals the limit as x approaches A from above of f of x, which is the right-hand limit. And I'll write it like that when we check. But the left-hand limit equals the right-hand limit if and only if the limit exists. The limit as x approaches A of f of x equals L exists. So this is one way to break, and we're going to use this theorem quite often to show that a limit doesn't exist. Because if we compute this and it's 7, and we compute this and it's 5, then the left-hand limit didn't equal the right-hand limit, so the limit doesn't exist. And then this will be the same with the positive and negative infinity, which we're going to do right now. Let's do one where we do a finite value, and then I'll segue into the reciprocal functions, which give us a couple different cases. So, example, the Heaviside function is another piecewise function using electric circuits. We're going to define h of x to be 1 if x is greater than or equal to 0, and 0 if x is strictly less than 0. So it's a piecewise function similar to absolute value, but it's just on and off. What's the limit at 0? The limit, so what I see is it switched at 0, so we have to check that the left-hand limit would equal the right-hand limit, otherwise the limit at 0 won't exist is what I'm going to check. Once I do that, why did I check at 0? Because that's where the function switched, and that's where I might possibly have a problem. The function is going to be well behaved. It's just a 1. What this function looks like is, and then I wasn't going to draw it at first, but if you look, it's just going to be 0 here, and then 1 here, but at 0 now you can already see from the picture the left-hand limit is going to be 1 and the right-hand limit is going to be 0, so the left-hand limit doesn't equal the right-hand limit, so the limit doesn't exist at 0. Everywhere else it will. It'll just be a constant. So the left-hand limit is equal to the limit as x approaches 0 from below of h of x, and then I ask myself, same as absolute value or anything else, which one do I pick? Oh, kitty. I'm going to sneeze. I pick, because I'm below 0, I pick this one. So that's the limit as x approaches 0 from below of just 0. Oh, excuse me, just a second. I gotta blow my nose. Get it. Oh, that didn't help. Oh, kitty, kitty. All right, sorry about that. Tail end of the cold still. Oh, my goodness. Okay, which is just 0. The right-hand limit is equal to the limit as x approaches 0 of h of from above of h of x. Which one do we pick? Now we're above 0. So I pick above 0, which is just a 1. So this will be the limit as x approaches 0 from above of just 1, which is 1. Because these don't equal each other, we can say if and only if the limit as x approaches 0 of h of x does not exist. The left-hand limit doesn't equal the right-hand limit, therefore it doesn't exist. Coffee. All right. Just making sure I got no boogers because I sneeze. Okay. Now let's transition into a couple of the Atari ones, and then we'll have the 4 kinds of limits down after we do at infinity. So case 2 was we're going to have f of x go towards plus or minus infinity possibly as x approaches a, which is still in R, and then we're going to check a possibly from above and below now. The first canonical cases are going to be these 3 cases, so let me draw these and we'll describe and just show in limits, and then maybe I'll end the video here and we'll do the next 2 cases in 4.2, which is going to be when we look at when we go to infinity. So you can have a horizontal asymptote, you can tend to a value, or you can blow up positive infinity. Those are the other 2 cases. But for now, let's do 1 over x squared and negative 1 over x squared. At near 0. So 0 is the problem in each case. For this one, we're going to see that, and I'll show you how to do this in general, but this is just to show us the idea of what we're using this symbol for. And so I can lean on here and drink some coffee. This one is going to say that the limit doesn't exist because the left-hand limit, the limit as x approaches 0 from above the right-hand limit, is equal to of 1 over x. We're saying, where does x, is x positive when x is above 0? Yes, this is going to say that x is greater than 0. And so this is going to say that we're going to go to positive infinity. They're going to write equals positive infinity, and they're going to cheat. They're technically saying that it blows up arbitrarily large. The next one is going to say that we're going to blow up arbitrarily negative. So this will be the limit as x approaches 0 from below of 1 over x. Now x is less than 0, so this thing is negative, so it's going to get close to negative infinity, which means it's just going to blow up arbitrarily large negative, is what we're saying with the symbol. And because the left-hand limit doesn't equal the right-hand limit, the limit does not exist. For the next one, what we have is the limit is going to, on both sides, are going to go to the same place, positive infinity, so we'll cheat and say equals positive infinity. So this one will be the limit as x approaches 0 of 1 over x squared is equal to positive infinity. And still what we're doing when we cheat and we say that is we're getting the function 1 over x squared is blowing up arbitrarily large positive in both directions as I approach 0. So we say equals positive infinity. And the same thing here, because it's going to negative 1 over x squared will go down in both cases. This one we would say the limit as x approaches 0 of negative 1 over x squared equals negative infinity. And still that's cheating. We're saying it gets arbitrarily large negative as you approach 0 from either side. It's doing this. So remember, we're describing the behavior of functions. Graphs of functions near values. So we did case 1 and case 2 this time. What that says is we are going to, in the first 2 cases we did, we're approaching a finite number. And then in the first case, we can use clever algebra or nothing goes wrong and we approach a finite value. Or we can have where it blows up and we have positive or negative infinity. What does that look like before we go in one example of how to actually compute? Let's do this. Those are the three canonical examples I use to show the cases that we're going to have. But let's try the limit as x approaches 1 of x squared over x minus 1. Then the first thing I see is, because I don't have squared, I am going to 1. There is a problem. We should switch and look at the left-hand limit and the right-hand limit immediately. So the left-hand limit is the limit as x approaches 1 from below of x squared over x minus 1. Why do I do that? Because that now gives me an inequality. This tells me x is less than 1. So that tells me, and then I can build this piece that I need. X minus 1 is less than 0. I just need the sign of it. So this is negative. And x squared is always positive. So this is a positive. So where I'm going is I'm approaching a positive over a negative, which says I'm approaching negative infinity. When I approach from below, I'm approaching negative infinity. What is this? Roughly speaking, we have it should be shifted to 1. And there's a problem, and what it's saying, what that just said is, as I approach from below, I'm doing this. That's what it just told me. On the other side now, what happens is, let me be lazy, and we're going to do this assessment. Nothing changes except for we're going to now do the right-hand limit. When I switch to the right-hand limit is going to say what now? This now tells me something that says x is larger than 1. So x minus 1 is larger than 0. So this thing is positive, and x squared, the other piece is, in this case I only have 1, the other piece is positive. So this is going to approach a positive over a positive, which is positive infinity. That was the assessment on this side. What it's